Here we are in Wollongong, the headquarters of the ANFF materials node. In particular, we're at TRICEP. It's a translational facility that was established through a partnership with URW and ANFF. Today we're going to look at our 3D printing capabilities that are housed at TRICEP, and here to take us through some of those capabilities is Associate Professor Stephen Byrne, and we're going to start off by talking about the Connex.
So yeah, we have a suite of additive fabrication or 3D printing tools here in Wollongong. This is one of the initial investments made by ANFF in 2010. This allows us to print in a range of different materials with inkjet-based technology, allowing us to get full density, high resolution components in a range of different materials, including biocompatible polymers.
So Steve, tell us a little bit more about how the actual printing mechanism works.
Yet, unlike most conventional or most hobbyist 3D printers, which would extrude a filament of ABS plastic or a polymer plastic, this system operates by jetting down small droplets of UV curable polymers and then curing them with each layer of deposition, allowing us to get 16 micron layer resolutions, watertight, gas-tight components, and like I said, in a range of different materials, including some robust, rigid, functional materials or structural materials, as well as biocompatible surgical guide-type materials.
And you did mention the resolution before. Is that in all axes, the X, Y, and Z?
No, that's not in all axes. That's the primary Z resolution, so that's the maximum resolution that we can achieve on the system, but realistically, X, Y resolution is probably order plus or minus 100 microns on a system like this. But depending on how you orientate your part, so basically if you rotate the part through three-dimensional space, you'll get that higher resolution in the desired plane.
And you mentioned the materials. I guess with a machine like this, the materials are somewhat limited that we can print.
That's true. The materials are typically proprietary materials that come from the suppliers. Most of the suppliers are expanding their material ranges, and of late there's been a huge expansion both in polyjet type materials and also stereolithography materials. It gives us much greater capabilities in terms of functional biomaterials.
So amazing range of capabilities. Can you tell us about our latest acquisitions in this area?
Yeah, so obviously our initial acquisitions were about 10 years ago. The additive fabrication space has moved on dramatically since then. A system like this would have printed in possibly maybe 2 different materials and then combined those 2 materials. There's now capability to print in full color resolution. Examples are multiple different printing technologies, both from Stratasys and from other companies like Mamaki, where we can print with the same high resolution but deposit colors on the surface to give you a much more realistic finished component.
And that must be very powerful in the field of printing medical models, for example.
It's very powerful across all the fields, not just medical models, and it does stand out in the medical model space, but also if you want to have a physical model of like a finite element analysis, simulation of a structure, you can have that analysis or the data from that analysis on a computer screen, but having that in your hand and actually seeing where the stresses and strains and forces are actually acting gives you a lot more feedback and visual information.
Yeah, it's an amazing national capability with really state-of-the-art equipment, and we're fortunate to be able to offer that to people around the country. And what are the types of projects that this machine's been engaged in to date?
So we've used this machine from over a huge range of projects, from artistic projects right through to surgical components as well as biomedical components. So one very simple example case here is where we were asked to take 2 commercially available components and combine the functionalities of those 2 components, so basically to allow a gas outlet off of 2 airway adapters and combine that into one physical component. We were able to take the geometry of one component and adapt that to incorporate a standard lure fitting that would then allow us to produce a series of these for use in a medical setting.
And what would you see as the major features of this particular approach to 3D polymer printing that would make it useful for people doing designs and prototypes, for example?
So one of the main benefits is that we have a sacrificial support material, and on later generations of this machine and indeed other systems that we have within the facility, those sacrificial support materials are water soluble, so you don't need to mechanically remove the support material. You don't even need to be able to access that material. You can dissolve the support material away in a fluidic bath. That allows you to completely expand the design. There are no more design restrictions. You can completely expand the design capability to have features that were never conceived of before.
And if someone wanted the team here to produce a 3D printed part, what would they supply to you to enable you to do that?
There's multiple ways in which we can do that. We can start off by a design collaboration where someone will present an idea or give us an overall concept of what they would like to do, where we would then design a component around those boundaries. Or indeed, they may already have a design and are just trying to access us for the fabrication capabilities, and both are fine. We're able to engage across multiple design platforms and softwares, as well as give advice on the most appropriate printing technology, as well as printing materials.
Yeah, and so traditionally in ANFF and most of the pieces of equipment, we have the option of either doing that, providing the design, and we create the component and send it to the collaborator or researcher around the country, around the world. Is there the option on sophisticated pieces of machinery like this for people to actually come in and get trained?
There is indeed. The training will be more of a holistic training in regards to the design for printing via 3D printing or additive manufacturing, and common considerations that we would have across each of our printing technologies. Then awareness of the materials themselves, the compatibility of the materials, any of the restrictions in terms of the printing facilities, so in terms of minimum resolution sizes that they can achieve, or indeed the compatibility of the materials to any post-processing that they need to do.
And like roughly, I know it's going to change person to person, project to project. Give us an idea of the training times involved there.
So we have experience of training complete novices who come from different fields, through to engineers with some experience in 3D printing space. A lot of our initial time goes into the CAD development and how you work around that. For experienced CAD designers, it's a very easy transition from classical design for manufacture through to new advanced fabrication techniques, and that's a very short education time period in the order of hours and days. For a novice user, we'd first start to train them on low-cost extrusion-based printers as we progressively step up into the more sophisticated technologies before we'd finally get to higher-level metal-based systems, which are a bit more outside of the confines of these simpler polymer machines.
And from what you've said already, obviously we've had a wide, diverse customer base, a collaborator base that have accessed this national capability. Do you see other opportunities for people to come in and access those capabilities?
Of course. There's no boundaries anymore to who can access us in terms of what area they're working in. So we would have machines that are working one day on jewellery components, the next day on producing jigs, fixtures, mountings and brackets, right through to the following day producing either three-dimensional electrodes or even biomedical implant type components. So we haven't found anyone yet who hasn't been able to find an appropriate workflow point where 3D printing can help in their systems, as well as not just the proven expertise, but the knowledge of multiple years. So there's 10 years of experience, and many of the same challenges keep on re-arising, and it's more so education of novice users to where the real benefits of 3D printing are.
Now we're going to have a look at some simpler approaches to 3D printing of polymers, and we're going to look at the Mark Forged instrument, and Steve's going to take us through that again. So Steve, tell us about the Mark Forged.
So the Mark Forged printer works very similarly to the normal FDM or extrusion-based printers that are on the market. This one has an added little bonus. First of all, it can print in a nylon-based material, so it's much more robust. It's externally weatherable, and it's appropriate for us where we want to work with any chemical solvents or organic solvents. The other benefit is that we can actually incorporate a carbon fiber filament throughout each of the printed layers. That allows us to dramatically improve the mechanical properties of the structures and give us really robust functional components.
And so even with this rather simple approach in terms of resolution and the number of materials, are there a wide number of applications for 3D printing using an instrument like this?
Again, this is another tool in the toolbox that we have here. We can use this tool for a range of applications, from surfboard fins right through to examples of PPE, what we've been producing recently in response to COVID-19.
Yeah, so that's been an interesting example for the ANFF materials node, for TRICEP, for ACES staff to be engaged in, where a local need, an urgent local need, was able to be met by using the facilities and expertise and that knowledge base that we have on campus here. So can you tell us a bit about that example?
Yep, it's a really good example, and it really shows where additive fabrication can be used as a stopgap measure. Additive fabrication is not going to compete with conventional manufacturing processes, but there's a lag in the time required to tool up for conventional manufacturing. So we were able to take a widely circulated design of a face shield mounting headband. We're able to produce that in a range of different materials and a range of different iterations to allow us to produce up to 3,000 of these units that were delivered locally into our local health system.
And this example also highlights the role of ANFF, the role of ANFF Materials and TriCep in bringing together local industries and capabilities to meet a need, doesn't it? And it happened incredibly quickly and cooperatively.
For sure. And the reason being is that we obviously couldn't produce that volume alone by ourselves on 1, 2, 3, whatever number of printers. So we were able to access local companies, including CamPro, who are based about 20 minutes south of here, and another company, another startup company called Me3D. They were able to put together or give us access to a larger suite of tools, a larger suite of FDM printers, which we were able to produce at a much higher rate, allowing us to meet that 3,000 unit target.
Yeah, and I think this is another really important role for facilities like this, is to help, particularly in the current climate, help industries establish and emerge and look for new opportunities and test out those ideas in a facility like this.
Yeah, it's been quite interesting to see how companies are able to pivot. So a company that's set up to work in the educational market and provide 3D printers to the educational market has now pivoted quite dramatically to produce face shields in large volumes.
So we've just had a look at all of our 3D polymer printing capabilities, or some good examples of that. And now Steve's going to take us through our ability to 3D print with metals.
So we've seen some of the polymer machines. A lot of the polymer technologies are a lot more well established than metal additive fabrication. Metal additive fabrication is a well established industrial process, but it does have some significant differences in terms of the material properties, in terms of the processes and the environments that you're processing within. It allows us to to achieve really high resolution detailed components, but there are some supporting considerations to think about when designing components.
And it obviously, like all 3D printing, builds things up layer by layer, but how does this actually work?
So the starting material is metal powder. The powder has been atomized to be spherical particles between 25 and 65 microns in diameter. In the case of this machine, the powder is screeded across a build tray, and the layer thickness is about 25 microns, and then a high energy laser with a very fine focus of down to about 10 microns starts to weld those particles together. So it rasters over the surfaces, welds the particles together, produces a layer. Build tray moves down 25 microns, the next layer of powder is screeded across, and then it starts stacking those sequential welds on top of each other.
And so tell us a little bit about the materials inventory that's available with 3D metal printing at the moment.
So initially people would start off with stainless steel as one of those more inert materials. It's very easy to process, especially on the more modern machines. We have a preference for titanium. The titanium processes very well on these machines, allowing us to produce high strength, high resolution components, and when there's a need, we can also produce components with biocompatibility. And
is there a change in the resolution available or achievable with different types of materials?
Yeah, that is one example. So the highest resolution material will be cobalt chrome, which is used for dental implants. Typically the minimum feature size that we would achieve in titanium or stainless steel will be in the order of 120 to 150 microns.
And what sort of applications or projects has the team worked on using this technology?
This is actually one of the best examples of the wide breadth of work that we've done. We've worked with local jewellery designers to produce some very detailed bespoke components, right through to medical implants and concept implants for medical devices.
And in those cases, would the external party or the third party, did they provide the designs and they were created here?
Again, we would have both example cases where someone has come to us with a concept of what they would like to be able to design as an implant, as well as predefined and pre-designed components that may indeed have been designed based on CT or MRI data, or conventionally designed components that have been produced by this means to allow us to achieve internal features or surface features that aren't appropriate through conventional manufacturing.
And Is the option available on an instrument like this for individuals to be trained to get up to a level where they could work independently in our facilities on their designs?
That certainly is a possibility. In most operations, we would have multiple people present, so broader safety considerations would mean that we'd have 2 people present within this lab at any one time, an operator who's operating the system, and then someone who's there to assist.
And I understand we have new capabilities that have been acquired recently that can do other things in the area of 3D metal printing that just expands our capabilities.
That's right.
Should we go and have a look?
We will indeed, yeah.
So tell us about this new capability, Steve.
So one of the limitations that we previously had was build volume. The build volume on the older machines are smaller, 70 mil in diameter, 74 millimeters in height. We've now expanded to a system that allows us to do 100 millimeter cubed. Okay? This also has a much higher production rate. It runs faster than the older machine. It has a higher energy laser, allowing us to get through more material quicker. There are a growing number of these systems within the country. A lot of them are held within private entities. This is an easily accessible system where third parties can come to us, access our knowledge, access our expertise in how you would set up a component or redesign a component so that it's compatible with this process so that they can get the final mechanical or material features that they want to achieve.
We are here on the Innovation Campus and we're going to have a look at 2 of our bioplotting capabilities. These capabilities are available through the ANFF materials node. And I'd like to introduce you to Dr. Johnson Chung, who's going to take us through those capabilities. So Johnson, tell us about the GSIM.
The GSIM is a multifunctional printer, so it's got interchangeable heads. We could exchange it for extrusion based heads, piezoelectric or melt electrowriting.
And piezoelectric is essentially inkjet printing, is that correct?
Correct. It's a drop-on-demand technique where you can place individual droplets, either cells or DNA, RNA, onto specific locations.
So that's a highly multifunctional printer. Can you tell me with each of those techniques what types of materials you could print?
So for the extrusion-based printing, because we have a hot melt extrusion as well as a low temperature, so we can print out hydrogels that require cooling. For example, alginate, gelatin, hyaluronic acid, collagen. For the hot melt extrusion, we could do thermoplastics such as PCL or PVA that goes up to about 100 degrees to melt. And then for the piezoelectric, usually we're doing very low viscosity inks that are mainly composed of cell culture media with cells or DNA and RNA.
Are all of those techniques amenable to printing with living cells?
Yes. So not quite, but for example, the hot melt extrusion, you can't put the cells in there to print, but that can be used as a structural material to place cells either in between or on top of these thermoplastics. This whole printer is encased in a level 2 biosafety cabinet, so all of the process in there can be sterile, so it's ideal for cell printing.
So with the other 2 techniques, the drop on demand and with the extrusion, you can actually print with the living cells in the ink?
Yes, you can actually mix the inks with the cells, so we call it cell-laden hydrogel, cell-laden materials, and then we print the structure with cells uniformly dispersed within that.
And then it's possible to create, using this particular GSIM printer, it's possible to create hybrid structures that use multiple techniques to create that?
Correct. I think this is where the unique bit about GSIM is that because of its interchangeable head, we can load different print heads, and within the structure we can use a hybrid approach to, for example, use extrusion to lay out the foundations of a scaffold and then decorate the scaffold by a piezoelectric function. At the end, if you do want to translate this onto a melt electrowriting sort of scaffold, which have much thinner struts, that's also possible.
And what is the resolution available with each of those different techniques?
For the extrusion-based printing systems, it really depends on the nozzle that we have. So currently, it's down to about 100 micron filament width. For the piezoelectric, where droplets are around 50 to 90 micron, so that's around say 50 to 900, about 900 picoliters is sort of the optimum resolution right now.
And what types of structures have been printed using the GSIM?
So for GSIM, we've obviously printed simple structures such as the cubes, but we also use this for coaxial printing. It has a coaxial head that some of the students are working on drug delivery patches, and also, for example, the metal electrode writing, it would be really thin scaffolds that has a lot of flexibility, so kind of like also like a patch.
And the coaxial head is around the extrusion printing, or both?
It's for extrusion only. So it has a particular head where we can put two materials, one in between the other, and then you can load your core with drugs or other growth factors.
Tell us a little bit about the 3D bioplotter from Envision Tech.
The 3D bioplotter is a extrusion-based printing system that is unique in that it can load up to 5 different materials at once.
When you say load 5 different materials at once, you mean those 5 different reservoirs?
Correct. So for the extrusion printing function, it has 3 low temperature extruders and 2 high temperature extruders, and so we can actually load 5 different inks and then have that on at the same time, or into a structure.
And these are plotted sequentially.
Correct. So they after you've programmed the printer to print one material, it then drops this cartridge and then picks up the next one, and then it continues its layer by layer fabrication process.
And you mentioned different temperature control. What does that mean in terms of the types of materials you could do from each of the reservoirs?
So for the printer, the low temperature cartridge can go down to close to 0 degrees. So it goes from 0 to about 40 degrees. And so that means we can actually load in hydrogels that require cooling. So for example, gelatin, alginates, hyaluronic acid, collagen. And then for the high temperature extruders, it can do up to about 250 Celsius. So that we can do PCL or some of the thicker sort of composites with graphene that may require higher temperature because it's very viscous.
And with the lower temperature ones, is it possible to actually print structures with living cells in them?
Yes. So this whole printer is enclosed in a customized biosafety cabinet. And so before we do a cell printing, we would clean the surface and make sure all your materials are prepared sterile. And then we would load the cells into the ink, into these disposable, and you can also sterilize these into these cartridges, and then we print the structures in a cell-laden film type of format.
And could you use this approach then to print different types of cells within the one structure?
Yes, because we have the option, for example, the low temperature, 3 of these different kits, we can actually load 3 different types of cells or 3 different types of materials into, and then print them into one single construct.
And what sort of resolution can you get with this type of printing on this bioplotter?
So again, for all the extrusion-based printing systems, the filament width is determined by the nozzle diameter. So we can go down to as tiny as 100 microns. The XY resolution on this machine is within 10 microns. It's very accurate. And then it also has a automatic leveling system. So depending on whatever the substrate is, whether it's a cell culture plate or glass slide, we don't need to manually determine the height. It will do it by itself.
Can you just comment on the type of training that people would have to go through and how long that might take?
So for this system, we do a group training initially of an hour as a group, and then because this system is only extrusion based, the training time compared to some of the other more complicated printers are much shorter, but we require the user to come back for 2 bookings of at least an hour each before we then join them for a sort of a assessment session where we can determine whether they can use this printer independently, and then usually after the 3 hour initially, they would show some sort of independency in using this printer. But to get really familiar, we would say at least 10 hours before you can actually do a good print and know the little features on there.
And being part of the ANFF materials node capabilities, researchers around the country, indeed around the world, have 2 options. One is to send us
designs or structures that they would like to have printed, and we can print that for them and make it available. Or they can be trained and come in and work as an independent researcher, then creating their structures in this facility. Is that correct?
Yes, that's correct. So if they want to give us some inks, we can help them print it out and give them the test results and the images. If they do want to get trained on this, we would then provide the same training we provide to all the other staff and students in the institute, and then they would be independently capable of using this printer, and we allow them to make a booking online.
So it's an incredible range of capabilities we have here in terms of 3D bioprinting, the range of materials that can be printed, the range of cells that we've demonstrated can be printed, and obviously something we want researchers around the country to use.
Yes, absolutely. This is a very robust system. It's got a lot of potential, and it's really easy to use.
The ANFF Materials Node, in partnership with ACES, has built a body of knowledge and expertise in the area of 3D printing. We have also established world-class facilities in the area of 3D printing. With the support of the University of Wollongong, we've established TriCep, a translational facility in 3D printing to help turn business opportunities into real industries. We are keen to work with you to use this amazing capability to turn your ideas into commercial opportunity.